Hello, I'm Harold Allman from translationdata.com. Today I've got a presentation by Mark Kegel. Mark's going to discuss how Scala Magic works on the JVM. It's part 2 of his presentation. If you want to see the first part of the presentation, just check for the videos on this channel. And if you like the video, please subscribe to the channel by clicking on the button below.
So this is the second half of our Scala decompiled lecture. So the last time we went through some of the really core constructs of Scala. So to pull up what we had in part 1, we covered val and var, def, how a val override of def works, lazy, class, case class, how lambdas are implemented, which are some really cool syntax sugar. They look sort of very similar to the way that Java ended up. We kind of looked at Scala versus Java namespaces and the fact that object is some kind of interesting magic. We looked at the primary constructor and how constructors differ in Scala than in Java. This is the second half of my warning of that. Scala constructors do look different. They don't operate the same way that Java constructors do. Specifically in Java, when you call your constructor, for those that don't know, the very first thing that your constructor has to do before setting any data, any of the fields internal to that object, is call super. That is a restriction that Java has. That is not a restriction that the JVM has. So when Scala implemented its constructors, the very first thing that it does is set its fields in the, I guess, argument list to your class, trait, whatever. Then it calls super, and what this allows you to do is actually do dynamic dispatch, basically invoke methods that depend on that data as part of your object construction. Now you may have never run into this problem, but it actually is a real problem in Java, and is probably the reason that half the factory methods out there exist, is because of this just silly limitation. Maybe it'll be lifted someday, I don't know. But if you see weird things like an object doesn't have a constructor up here, that's probably why. We'll dig into the bytecode and actually show that yes, it's doing stuff. It's just the decompiler that was bad. So, all right.
All Java goes to bytecode, but not all bytecode can be converted back into valid Java.
Right, right.
Yep.
So, like last time, we're going to be using bytecode viewer. So this time around, I'm not going to, okay, so for those not familiar, there's actually a bunch of different Java decompilers out there. I'm going to be using a Java decompiler because I sort of assume that people here know Java and can speak that, and that they don't necessarily know Java. So I'm doing this for the other reason that Scala very much values interop with Java. For as much as Scala is a functional programming language, it is not necessarily a dogmatic or zealous functional programming language, kind of the way that Haskell would be. So for example, any reference on the JVM can be null. Well, in a pure or strict functional programming language, that always has to be checked for. Now you can compile your stuff away. Your compiler can make checks and guarantees and say that, yes, at some point this reference has already been checked. I know that it's not null. But anything coming from Java land could always be null. Scala does not enforce those checks. It says that if you give me something and it's not null, I'm going to blow up in the same way that Java does.
It is.
So it's not strict in that way. The nice thing about that is that calling between the two languages now becomes relatively seamless. You don't have to do anything special to call from Java into Scala or from Scala into Java. All right, so let's look at Scala decompiled part 2. This is now, I think, up on my GitHub repo. My GitHub repo is this right here. All of the presentations, source code, and other things that I've given over the past, I don't know, 6 or 7 months, will eventually end up here. Right now it's only the code, but eventually my presentations, slides, whatever, will end up here. So if folks want to follow along, I will make sure that this has been pushed. Okay. And that. Okay, everything has been pushed. So if folks want to grab that, it's this right here. And I will give folks a few seconds to do that.
Yeah. Give me time to touch.
Can you make the text a little bit bigger?
Not maps.
Scala Dash enthusiasts? Yes, I got it. Beaker's the lead entry, right?
Yeah.
Okay, good. All right, thanks. I'm gonna post that on the meetup. So anybody who hasn't got it to it,
I already did.
oh,
That's
good.
literally what I was doing.
It's not show on tonight's, or did maybe
Yeah,
we do a
yeah.
refresh?
So
Just pushed it.
There it is. Okay, good. Thank you.
Okay, so now everybody can follow along, and I don't have to worry about folks getting lost. Excellent.
That assumption might not apply totally.
Okay, so last time we had seven different modules that I wanted to get through. Tonight, we actually have 12, and one of them is a two-parter. So we will try and get through as much as we can, but the first 5 or 6 are really covering info that we saw last time. So if you weren't here last time, we'll catch you up a little bit on what some of this stuff looks like. So the first module that we're going to look at is just how a simple class in Scala gets compiled down. And so by a simple class, this is really what I'm talking about here. Can everybody read that to a reasonable extent?
Yeah. Yeah.
All right, excellent, cool. So by a simple class, this is really what I mean. There's no horrible amount of magic here. We have a couple of parameters in our constructor. We have a couple of fields and a method that we've defined in our body. When we compile it, we get the expected thing. We get one class as an output, which is kind of nice. So if we decompile that, what do we get? Okay, so we see some strange stuff and some expected stuff. This is what it would look like if we had written that same code but in Java. So it should be more or less equivalent. We have an odd thing up here called Scala signature. But our class is named C1, which is good. We have internal fields B, C, and D. But if we look at the code, we kind of have to wonder where A went. But A is a method, so I guess that's not too surprising. And what we don't see is anything being a public field. So one of the differences between Scala and Java is that in Scala, everything becomes a method access. It auto-generates sort of your getters and setters automatically for you. So for example, this field named B in the background, which is a var int, it's actually generating the int right here, but your accessor is named B as well. So this sort of demonstrates the difference between namespaces in Scala and Java as well. So you can have fields named B in Java and methods named B in Java, and those don't clash because they live in different namespaces. In Scala, all of those things live in the same namespace. So if you have val B and def B, that's a name clash. So that's one of those things that you have to keep in mind. here's our setter, which looks a little bit weird. If you don't remember from last time, Scala very much abuses dollar to mean different things, and has lots and lots of wonderful compiler bugs. Don't ever use dollar for anything ever, is my advice.
Yeah. You want to bring the wrath of God upon you.
Okay, and if we're kind of looking at this a little bit more closely, we'll see that B is the only one with this special method signature. It's the only one with this dollar equals. C and D, which were defined as val and val, which is the equivalent of final, they don't have that dollar equal. They only have those getters. So now we sort of see like the val var kind of stuff. You can understand how it's implemented. It's just, oh, there's an extra method for vowels. So it's not really the equivalent of final. There's extra magic that's going on. Okay, and let's go look at our constructor just to prove to you that other interesting things are going on. I don't think there is. Is this actually decompiled? But one of the things that I am using tonight is a different decompiler. So tonight I am using Procyon, which made it look just a lot nicer than the JD GUI. Somebody last time reached out and said to use CFR. CFR handles some of the newer Java 8 features a little bit nicer. And there was a reason that I wasn't using it, but I don't remember what. I think it was just aesthetics. So,
What do you think about Java 8?
Java 8 is a wonderful addition to the language. I really hope they continue. I think Java 9 is going to slip. There was some noise today about the module stuff, Project Jigsaw not being ready.
Yeah.
And so, I don't know. For the most part, I don't care, because I wrote Scala.
Yeah.
And Scala at this point can target Java 6, Java 8, as well as a host of other backends and platforms at this point, JavaScript, and now there's the native backend as well. Okay, so we have some fields, we're doing some stuff. We load some references, we save them off. And you can see right here in the bytecode that we're actually doing those, we're setting our internal fields before we call super, which in this case is init on object. And then we actually do something else, which is to basically fulfill the contract of our method body, which is to say put field.d down here where we set that equal to 4. So what we're doing is we're doing this first, and then setting this, and then of course this is a method that's just going to return a constant. So, everybody understand what's going on and why this code looks like this Java and has that bytecode. Shake your head, I don't know. Okay, it's going to get a lot worse. Okay.
Yeah, if you don't speak up now, there'll be more detail later.
And really, if you have questions, please stop me and ask.
Okay, how do we know that it's returning 1? I mean, how come?
Okay, in def A, like how do we know that the method
when
named
I call
A returns?
class C1, I get the return of 1.
Right there.
Okay, so if you call
Oh, I see.
that, it's going to be this method right here. It just compiled down to return a literal 1.
Okay, yeah. Okay. So by the compiler, by the decompile, we know that, but just by looking at it, how would we know?
What do
You know what I'm saying?
Oh, like how do we understand? Well, you just have to have a mental model of what the Scala compiler is going to do. The Scala compiler is really smart. So if you have a literal in your code and it can just return a literal 1, that's what it's going to do.
Okay,
So like there are rules where it's going to box that 1 because it has to. But in this case, it carries that type down and it knows that it can unbox it.
okay.
Yeah, so the question is, if you're in Scala and you're writing in Scala,
Uh-huh.
you don't necessarily need to know this. This
Okay.
would be if you're going to either do Scala interop with Java,
Right.
or you want to understand how the compiler is operating because you've got edge cases you're trying to deal with.
Yep.
So, yeah, that's what all this is
Okay.
about. This is edge cases and interop. There's, I only do Java, I won't do any Scala. I mean, I won't do any, I only do Scala, I don't do any Java interop, or I just use Java libraries, but I wrap them with Scala. So for me, this is enjoyable to see what's going on, but I wouldn't actually need to know any of it to continue working.
Okay, all right.
So this is our second example, and it is just a simple trait. What does this code look like? So for those that don't know, traits are a more powerful abstraction than Java interfaces in that they allow you to have code. They also stack in a linearized order to give you some facsimile of multiple inheritance, which is really, really nice.
So they're like Java interfaces with implementation.
Well, so Java 8 interfaces can now have implementations. The
I
thing
didn't know
about
that.
traits,
Static
yeah, they are static only. Yeah, and this is actually much more like a class. Traits can also extend classes. Traits can extend other traits. Traits can stack. Traits can declare themselves only stackable on top of other objects. They are a much, much more powerful object design. They are capable of much more powerful design. So they also let you implement the type class pattern, which we will see how that's done later on as well. Okay, so this is basically looks like a simple trait that has a default implementation, so it's trait T1. It defines a method foobar that returns 1 by default. We define a class B that extends T1 and overrides foobar to return 42. So we know from the last example that we're going to get a class that does more stuff, and we know that we're going to get one file. Now, the nice thing in Java is that you generally have this one-to-one relation between the number of classes or interfaces that you have and the number of files that you get. When the Scala compiler runs on code that looks like it should have 2 objects, we end up with 3 files. So we're already deviating from like what Java is doing. So there's some magic that's going on. So let's dig into what this magic might be.
Now, this is pre-Java 8, correct?
This is pre-Java 8,
So-
we're doing 2.11 right now.
Yeah, good, right. 2.12 changed this, but we're not in 2.12.
And Dottie will change it yet further.
Yes.
So yeah, it'll be all kinds of fun. Okay, so we see class B implements T1, which is interesting because you can only say implements if T1 is actually an interface. So now we know that the Scala compiler must be generating something that really is an interface as far as the JVM is concerned. But interfaces in Java 7 and in Scala 2.11 cannot have code. So our next question is, where the hell does that code live that we just read? Where does foobar actually go and return 1? Because what we see is a method foobar here that returns 42, exactly like we would expect. So, well, I guess it's an abstract class, but I think that's the decompiler being weird. So here we have a method foobar, which returns 1, because it's an abstract class. I wonder why it synthesized it that way.
You know, I was about to ask, earlier you said the trait is more...
Oh, right, I remember this. Because here's the interface T1, and this guy is T1 class.
Oh,
He's not actually named the same thing. And
But it doesn't inherit the interface either.
no, he doesn't.
It's just the implementation, a static, oh, it's a static implementation.
Yeah.
Got it.
Remember this?
Yeah,
So
that's
it's-
right.
All of these are static, and then it's an abstract class, so you can't instantiate it.
And that's why this is being passed into
Yeah.
all of them. Got it.
And then what we see is that if you were to reference, and actually I just as well recompile this and edit it. if we don't make this override, okay, why is this not doing this?
It's not loading it?
There we go.
Okay.
Apparently I have to close it. It
Uh,
doesn't work very well. So now if we don't override it, now the Scala compiler itself is inserting a static reference to that method where we would expect it. Which
passing
is kind of
this,
crazy.
which then passes this, that gives it the context to operate on it as though it was local.
Yep,
Uh-huh.
exactly.
Yep. That's really
Okay.
cool.
And again, this is all magic that we covered last time, but again, if you weren't here, yeah, it's kind of mind-blowing. See what's going on. So now a stack trait. This is something that we didn't really see last time. So let's look at the code. Here, this is one of the things that's only actually possible in Scala. And this actually demonstrates linearization of traits. So you can see here that we have a method foobar in T1 and a method foobar in T2. We define a class B that extends T2, and so this class B should look exactly like what we would expect it to, what we just looked at. But here's class A that extends B with T1 and T2. So the question is, and this, you know, if I were being a really evil interviewer and hiring a new Scala dev, I would ask them, what is this going to print?
Right.
And I don't actually know off the top of my head. That's not true. I guess I put this together. So I do know what it's going to print.
Well, linearization says you read from left to right on priority, correct?
Yes.
Okay. Okay. That's the answer, right?
Yeah.
Okay, good.
It is.
Okay.
Yeah. So our super here is going to be B, and we know that we're going to get 42. The question of why is that? What is linearization? Read a Scala book. The basic idea is that it will pick from left to right. So if you have, for example, just A with T1 with T2, then it would pick the foobar method out of T1 because it's leftmost. And if you want the other one, then you just swap the order. That's how multiple inheritance is achieved.
And resolves the diamond problem at the same time.
Yep. Well, I mean, in order to achieve multiple inheritance, you have to have some solution for the diamond problem. Otherwise, you're just C++ and all that.
Well, that's what I meant. Yeah, well, C++ did it without solving it, left mess, right?
Yeah.
Right, and so, yeah, exactly. Linearization is the solution for that problem in Scala. Are there other is any other language doing that?
Yeah, .NET has explicit interfaces, so it just sort of like namespaces it. So you have like, you can implement both interfaces with the same name.
Yep.
But you just have like a namespace in front of it. You say this interface, you know.
Oh, so you're concretely saying which one you're pulling
That's a
through.
very C++ way to
Yeah,
think
okay,
about the problem.
yes.
In C++, you can do the same thing. Kind of.
Okay.
Very cool.
Okay.
But you wouldn't, if you're like casted to the interface, then you don't have to namespace it.
Okay.
It's like when you consume it, you're not namespacing it. But when you define it, you are.
So as a client, how do I know which as a client I have to specify the particular interface?
If it's casted to that interface, you don't. If it's not, then you probably do, or you have to cast it to the interface. Say like what I'm talking about, this one specifically.
Okay.
So if you take in like as a parameter, it's a specific interface, then you don't have to do anything. It'll
Okay.
just know which one to use.
Okay.
Okay, and if we wanted to answer our question just by looking at the compiling code about, you know, which foobar are we going to get when we call A, well, we can actually see that we're going to get T1.foobar. And if we swap the order, oh, that's interesting. So it's not actually B, it really is
Yeah, T1.
It's not the
It's
classes,
not-
And
it's
it's
the
not the
traits.
classes, it's the first traits.
Yeah, that's fascinating, because I had thought it
Yeah, 'cause I thought you were
incorporated.
saying that.
You can only extend one class anyway, right?
Right.
So what's interesting though is they leave it off the list, so I didn't know that. That's
Huh.
a subtle little,
Yeah, all kinds of gotchas. That's interesting. I wonder if it's because it is defined as a method in a trait that it would do that. I wonder if there was like some weird
So
abstract.
it gives you T2 or T1?
Gives you T1.
so if you
That's-
did not override in B, which one would you get?
It wouldn't matter.
You would still get T1, it wouldn't matter.
You would get T2.
You do not, well, so do you get a compilation failure when you compile class B with no override?
No, because you have a default implementation. In both of these, you don't have to override anywhere.
Yeah, you don't have to override.
I
You get
see,
T2.
yeah, I see what, yeah, I got you.
Yeah.
All kinds of fun.
So the extends B doesn't matter, it's just T1 and T2 that are linearized.
Yep. Which is kind of bizarre to me. I expect B to be doing stuff, but I guess not.
Is there a
Well, it makes
specific
sense
way that
because-
you have to say, Class A extends B, since Class B extended T2, do you have to say with T1 there, or can you say with T2? with
That's
T1?
optional. If you want your class to implement that interface, you can call that there, but it's not required.
What I meant was, can you switch the T1 and T2 on that Class A?
That would then switch the linearization. So,
You can do that?
yeah, you can.
Yes.
Okay. Wow.
Pardon me. Okay, so now we have our 04, which is a trait that extends a trait. So we saw a class that extends a trait. Now what happens when one trait extends another trait? Again, Scala can do interesting things. Let me just do that first place. That up again. Okay, so we have a trait named printer, which defines, with no default implementation, a method named print. And then we have a constant printer, which extends printer, overrides the method, and just returns a constant named constant. So let's look at printer real quick. Because unlike the last time, this time we don't get printer $class. We don't get a synthesized class. So the Scala compiler is smart enough to know that you don't have any code to stuff in a synthesized class, leaves it off entirely. So you just get the interface this time. Which is kind of cool. Here is the interface for constant printer. Something to notice here is that the names that we're using are really Java friendly. So like the way that we think of a trait in Scala would be with that interface name. If you're going to access it from Java, you can just use the same name. You don't have to know about any of the magic going on underneath, which is really nice. And then here's our implementation, which goes implements it as the static method that we expect. Okay, cool. Now, close this real quick. Here's the fun one. And the one that we really, really didn't see last time. There are all kinds of bugs about doing this. I don't recommend it, but it's technically a capability of the language. Traits can extend classes. So unlike Java, you can now build up something really interesting. You can build up an object that inherits from two different classes as long as you have proxy traits in the middle. It's entirely possible to do this. There are all kinds of horrible bugs that occur when you do this. Don't do this. Just go look in the Jira backlog for like 15 different things. But let's look at how it's implemented. I honestly don't know.
What would be the reason to do that?
if you
existing
really do want
implementation?
to pull in this sort of interface of that is that class. Or if it's fine, well, if it's final, you can't. But I know there are reasons to do it.
Okay.
And, I don't know if you really want is instead of hasn't.
But, yeah, wow. I'm just trying to wonder why you would want is instead of creating your own interface and then do
Compatibility
delegation.
too with Java APIs, where you want to extend some class and you're going to pass it back.
I see.
So now you've implemented that quasi sort of, but I don't know what it's going to look like on the JVM, so I don't even know if that's going to be possible.
You could get a Java class and want to extend it with a trait in Scala. Maybe that's more the thinking.
That might be, yeah. Oh, but we didn't actually look at the code. The code this time is, instead of printer being a trait, printer is now just a class. That's the only thing I switched.
Is that a typo on the printer class? Def print string equal
No,
S?
that's correct.
It's supposed to have an S in front of it?
That's for string interpolation. So, I guess I just left that in. But that is not a typo.
Okay.
But it does make it look weird because it
It
introduces
looks-
a string interpolation context for zero interpolation at all. Oh well,
Oh, it's probably a default pattern.
yeah.
Mm.
Okay, so we end up with a class. We know what classes look like, and this looks like what we would expect Scala to produce. But with constant printer, what do we see? Okay, we see an interface that's the same thing, which is kind of weird. So that means that constant printer, that interface, does not extend from printer. So now all of a sudden we've broken that assumption that we could inherit and pass it back, and it's actually extending that other class. So Scala's lying to us in terms of what interop capability it can actually do. Keep that in mind. So if you have a trait that extends class, it's not extending that class. It's lying to you. Okay, and then here's print, and then here's init as the implementation of the static methods as we would expect as a trait. As well, constant printer is now a trait. Okay. Did everybody follow that? Or did it at least make sense? Did I sort of explain what the issue is in how Scala is lying to folks about what the capabilities are?
Wait, so basically, if you overrode the abstract method in the class, it would not actually override it in the trait, is what you're saying.
No, it would. It would override it, presumably. It would figure out a way of doing that. It would probably have to synthesize something to do that. But the point is, the interface, the Java accessible thing that it's generating cannot lie to the JVM about the type of object that it is.
I see.
Because with the code that we've written, if I have a constant printer, in OO parlance, I should be able to pass that in to any method that accepts a printer, right? The way that this is implemented, I cannot do that. That breaks OO subtype.
Or that's the list of substitution principle. That breaks that.
Yeah, basically, yeah.
Okay.
So all of a sudden, it doesn't work the same way. It's probably okay in Scala land because it knows what it's doing here. But all of a sudden with interop, I can see this getting really, really nasty.
Mm-hmm.
Okay. The last one is object extends trait. If you're not familiar with Scala objects, they implement in a first class way the singleton pattern. So that you don't have to go implement all of this stuff. But then, because they do that, they bake in some additional magic that we might actually get to see towards the end of the night. So let's file that. Okay. Here's our interface printer. Again, we have a trait printer, method named print. And now it's just an object constant printer that extends printer. And it's because this method is not defined, we actually need to provide an implementation. And we do that right here. So if we look at printer, again, it's this trait, it's there's no synthesized class underneath, it truly is just this interface. And then if we look at constant printer, we see some weird stuff going on because now all of a sudden it is an object. So when I call print on an instance of this class, what I'm actually doing is calling off into this module dollar thing and calling a static method on that. And that lives up in constant printer dollar, which is a synthesized class that Scala is giving us, which looks very different. So this is the class over here that actually implements printer. So now all of a sudden our OO subtyping relationship is restored, but it's of a class of a different name. So all of a sudden the Java niceties about what it's telling you is the right object name go out. So now the actual class name is going to be ending with a dollar. So if you were to look at a Scala stack trace, you're going to see a lot of dollars if you're using a lot of objects or lambdas or other things. That might throw you off, but now you know where it's coming from. It's coming from all of these synthesized classes because when you get a stack trace on the JVM, it's thinking that it's Java. So it's going to look like this. And that might throw you off. Okay, so how are we implementing the singleton pattern? Really simply, we just have a static constructor in our static block. We knew it right there. That obviously can't work. So
Somehow it's,
right, it's calling this down here. Because that's our constructor.
oh, got it, and that
It's
then
setting
puts it
model.
back in the static context. Yep, that's
Yep.
it, that makes sense, that's the loop. And
So now
module
what-
dollar is technically a variable name that's being assigned this and it's defined up above. Got it.
Yep. So now it has a method that we can actually call on to. This pattern we see all over the place anytime there's an object. There are companion objects for case classes, and I think we'll look at some of that maybe tonight. I don't remember. So, all right, so that's about half the content that we had for tonight. So, any questions so far about what you've seen? Any concerns about using Java if you don't, or using Scala if you're not a full-time Scala programmer? All right. Don't let this deter you, please. I don't want to throw people off using Scala.
I have a
All right.
question. Earlier you had one of those with double extends with. In that one, you returned T1 instead of T2. Why was that?
Oh, so that's the linearized.
Yeah.
Linearization.
Yep. Which one was that?
Number 2, wasn't it? No, that's stack trait. Number 3?
Yeah.
There we go.
So your question was, why does super point to T1 effectively?
Instead of T2, yeah, because T2 is at the end.
So this is the linearization rule that Scala has. And the rule is the method on the leftmost trait is the one that wins. And it's an arbitrary rule, and that's just what they picked.
So we can have like 100 afterwards and none of them matter.
Yep.
Okay.
And what this allows you to do is actually have T1 and T2 both inherit from the same trait, implementing the same set of methods, and now you can choose which method wins by the way that you construct your object. And this is actually the stacked trait pattern. It has a name, there are lots of use cases for it.
In general, you would avoid using it, right? Only because it's...
Not necessarily. I mean, I've had a couple of occasions of wanting to use it.
Oh, okay.
So.
I have a question. Do you have to put the with T2 since Class B already extends T2?
You don't have to, no. You would actually be able to pull in the same methods. But by doing that, I can now pull in an arbitrary set of traits. And so I can
So
actually
could you not still
override.
access the T2 since B extends it?
There might be a way to do that. I don't know what that syntax would look like.
Wait a minute, if you do that, that puts T2 in front of T1, because B's extending T2, and the
Yeah,
way
if you
any class in place automatically is replaced by itself and all of the things that it inherits before the list continues.
So if you left that with T2 off, it would,
Then it'd be implied, extends B, and then extends T2 with
so T2 would
T1.
win.
Yeah,
Okay.
so T2 it would reverse the order by the, so that, when you did that, you forced it back out to T2.
Interesting.
Oh, so you're saying the linearization is reverse here if we remove T2?
That's what at least according to what I just read.
Really?
Yep. So, and it's weird, the way the linearization works is it's A, and then it's T2, T1, B. That's essentially, it flips. Actually, the class may not be flipped out, but all of the traits flip in. In other words, you can determine the order by taking everything that's withed and list it and then reverse it, and that's how it proceeds. It starts with the class and then goes through each one of those traits.
Yeah, I knew linearization was weird, but
There's some weird rules in it. We probably don't want to dive too deep because you could spend all evening on it.
Why don't you go ahead and remove T2 and compile it?
yeah, that's what I was going to do.
I think your flux settings affecting the display.
Oh, yeah.
It's getting dark, so.
There we go.
Ah,
Yeah.
Oh, that's a lot better, Mark.
Oh, good, good.
So it did get T1,
yes, still got T1. Interesting.
meaning T1's at the end of the list.
So basically, the traits of a parent class don't matter.
Well, no, so what happens is,
Inheriting.
as you go through the list, the first thing you can do is extend the class. That class is basically replaced with whatever it's inherited. All those get sucked in as though they were, you had said B plus whatever interface, with whatever interface, with whatever interface. And then, as you pop back up again, when you do the with and you grab a trait, you're just adding them on. Once you have that list, you take all the traits, you reverse it, leaving the class in place, and then it basically goes, is what I'm calling in B? No. Is it in the trait at the very end, which wasn't in B? And is it in this trait, which wasn't in B? Okay, is it in this trait that was in B? And that's how the resolution occurs. Actually, I'll post a little link. I found something that goes into it. You'll see the rules on linearization and go, oh, you know, I don't really think I care to know about that now.
So when you take them all off, it,
So if we take them all off and just say A extends B, now it's,
now it's going to go to the T2.
well, no, it's going to go to B. So
Oh,
B is my super pointer, right?
right,
So it's going to go to foobar and B. So now we need to look at B.
and B does T2.
I just posted it up on the meetup if you want to go look at that.
And B has its own implementation, so we get the right thing. We get the one out of B.
Okay. Interesting.
Which is kind of interesting.
Yeah, this has been, they have gone over and over and over and over this.
What's interesting is that, yeah, is that if you don't put T with T2 there, then that's just totally ignored, basically.
So now, if you added a trait to some object, and it happened to implement a method that had the same signature, you could stomp on some other indirect, in an object in some indirect way,
Right.
I guess is my point. I know that fact has been pointed out in the past, but seeing like why that is kind of interesting. Okay, so that's all of the OO stuff. We can see how, we're synthesizing objects, we're creating classes that don't really exist anymore. We're lying about what our OO capabilities are. So if you need to call from Java back into Scala, you can see how things are a little bit more interesting. The rest of what we're going to be looking at are features that we're really just wondering how they're implemented in Scala. So pattern matching, for comprehensions, implicits, and some of the shapeless and type class stuff, you're never going to have to worry about these features from an interop perspective. You might more have to worry about them from a performance perspective. So let's go look and see how, for example, pattern matching is implemented. So here's the code that we have. We have an object named match, so we know that we're going to get a couple of things that look weird off the bat when we compile those. We have a case class bar, which we haven't looked at before, but a case class, for those that don't know, is a really nice shorthand way of defining sort of a data class within Scala. So the syntax here is just putting case in front of class. You can have a body, but typically you don't. And everything here in the constructor list, those will automatically become vals. You don't have to say val and prefix that up front. And now when you construct that class, it's immutable. You can create copies of it. And so there's all kinds of interesting like hash code and toString and extra helper methods that get generated by using a case class. But all of that magic is done by the compiler in the background. So it's one